Look at this split-screen comparison. If you want to build an AI prompt generator that spits out every possible combination of keywords, your first instinct is to hard code a series of loops. It works for a small, fixed setup until you are wrangling 5 deeply nested loops that are impossible to read, compared to a compact 10-line function. The moment your keyword dataset scales or a user requests a dynamically changing sequence length, that nested structure shatters. You cannot write new loops into your code while the program is actively running. This diagram shows the solution, a depth-first search equipped with an undo button. In algorithm design, we call this backtracking. Instead of physical loops stacked inside one another, backtracking relies on dynamic recursion. The algorithm plunges down the branches of our decision tree, picking one keyword after another to incrementally build out a single, valid combination path. By utilizing recursive depth rather than rigid syntax, backtracking generates all valid arrangements without breaking your architecture when the variables inevitably change. This diagram illustrates our algorithm's engine, the state container, a shared memory array tracking our active keywords. The framework starts with the choose step. We take our first candidate keyword, creative, and append it to the shared state. Next is the explore step. The function calls itself, diving one level deeper into the recursion tree. To ensure we don't reuse the exact same keyword we just picked, we pass an advanced index, i+1. The recursion repeats these steps to the bottom of the tree. The word tech drops in, and we successfully yield our first valid combination path. Hitting the bottom is only half the algorithm. The core mechanical challenge is navigating safely back up the tree to explore alternative sibling branches without corrupting the data we hold in memory. Consider this. When the code loops to the next keyword, what happens to our container if no cleanup is performed first? Old choices permanently mutate the shared state and bleed directly into new branches. The word audit crams in alongside tech, instantly poisoning our array with an invalid sequence. This specific bug, known as state leakage, triggers 0 compiler errors. Your program will run silently and output completely invalid permutations. We fix this with the unchoose step. By popping the last element off the array the moment a recursive call returns, we cleanly reset the shared state. Tech is erased, leaving a pristine slot for audit to fill. This mutate then undo sequence defines the backtracking pattern. We execute a single line of cleanup code, and in return, we maintain a highly efficient recursion stack memory locked at O at n. This animation highlights our final pitfall. When we reach the base case, we need to collect our valid paths into a final results array. But if we append the state container directly, we fall into the reference trap. Saving a direct pointer to a constantly mutating array means the final output list emerges completely empty, or full of identical, corrupted duplicates. We solve this by taking an explicit snapshot. We generate a deep copy of the path at the exact moment it becomes valid, locking those values in place before depositing them into the results list. Because we are generating every possible subset, the theoretical limit for time complexity is O of n times 2 to the power of n. The exponential volume of branches means we must aggressively prune invalid paths early on large inputs, or the calculation will never finish. Solving combinations predictably relies on a strict 3-step rhythm. Choose to mutate the shared state, explore to recurse deeper, and unchoose to revert the state cleanly. Apply this blueprint and exponential problems become entirely systematic.